good? It's good or bad? Looks like we're live. Oh my. Oh boy, oh boy. Oh boy. I don't care if my bitrate is bad. I'm streaming, damn it. I don't care what anyone says. Okay. Hello. I'm Alistair, if you haven't guessed already. Today we are going to be going over some of the, wow, I am, sorry, my brain's fried apparently. But we're going to be doing some Lambda Calculus stuff, which is a super cool language that you can use. And there are some online interpreters, but if you want an interpreter of your own, I wrote mine. Here's my little plug. You can go over to this link. It's also in the description, I believe. Let me check that. Yeah, it's in the description. So you can go and you can check that out. And you can download the source and you can launch the little REPL thing. Let me show you that. So your folder will look something like this. It won't look exactly like this because this is my version of it, right? But this little Python file, if you run it, which is called REPL, it'll bring up this thing right here, which is your little interpreter thing. So you can type in an expression like, oh, this. All expressions need to be ended with a semicolon. So this will give you back 3. That's correctly evaluated. You can make variables in it. Oh, this is a depressing song. Oh, I'm so depressed. Oh, depressing. Less depressing. So you can have this, for example. And I could be like, oh, what's 3? 3 is 3. The identity of something is itself. Ooh. So, but I can test multiple things, like ID of 3, ID of 4, and it'll run each one and give me each answer. So that's pretty cool. If I go, what's ID of ID, it just gives me back ID. So that's pretty neat. So, and you can, and there's some special operations for leaving the interpreter, debugging, and loading your programs. But I'm running it through the command line for editing purposes. And if you're on Windows machine, I'm going to warn you, that lambda symbol you saw, let me show you that again. This thing right here, this is lambda, lowercase lambda, it's a Greek letter. This will not show up if you run this through the command line on Windows machine. Let me show you that it doesn't. Open up, and it's just this weird square instead. That's because Windows, the command line, doesn't support Unicode characters. And the lowercase lambda is a Unicode character, so you can just kind of cry about it. But I'm going to be using that. If it bugs you, you can also cry about it. Real quick, let's talk about what Lambda Calculus is, and let me give you some examples. Let me open up my favorite program, which is Paint. So I can, typed in Paint, got Python. It's not wicked. Guess I would like to paint. So, let's go over some simple Lambda Calculus, okay? Calculus being just for computation, a way of doing math. Okay? It's made by a cool dude named Alonzo Church in the 20s and 30s. It's like 1930s, I think. But if you know what substitution is in math, then this is going to look real simple. There's only really one value in the Lambda Calculus, and that is functions. Now, in algebra, a function looks something like this. You know, f of x is equal to, let's say, x. So this is the identity function. If I wanted to use this function and plug values into it, I would have to do something like f of, say, 3. And what I do is I substitute 3 for every x in this bit beyond the equal sign, which is called the which is called the expression, excuse me. So you'd have this, and now I've substituted all the x's. What I do is I just take all of this beyond the equal sign as an expression, and I try to evaluate this. In this case, the expression 3 evaluates to 3, so the result is 3. Pretty, not that difficult. Lambda calculus looks a little bit different. It looks something like this. I'm going to use lambda. So lambda x dot x. Okay, looks like this. And now, so real quick before I can add, well, if I want to do f of x equals x of 3, I would, in algebra, if I was doing f of x equals x, if I wanted to plug in a value, I would have to do substitution, right? In the lambda calculus, it works for a similar way. So the rules for lambda calculus is if you have you're trying to evaluate the leftmost value on, like, imagine like a piece of line paper, right? So this is on one of those lines. You're trying to evaluate the leftmost function. In this case, this is lambda x dot x, right? So the way you go about evaluating a function is you look to see if there are any values to the right of it. If there's a value to the right of it, and this function takes a value, in this case this function takes x as a parameter, then what we do is we substitute all the x's in this part and in this part for 3. Okay? So there's a couple of pieces I need to talk about in terms of anatomy of the function before we can use it. This part right here is called the head of the function. It's the function head. It basically, this lambda basically says this is a function we're defining, and this x is just saying we will take in some value that will be substituted for x. All of the code past this period is called the body, or the body. So during substitution, what we do is, let me show you that in action. So we're going to take 3 and we're going to substitute it for all the x's in the head and in the body. So it looks something like this. Lambda of 3 dot 3. And now the 3 is no longer there because we used it up. But now, since there are no other variables that we've used, such as x or y, what we do now is we will toss out the head and this period. So we'll get this. And we'll also remove this and parentheses. So as a result, what we get after tossing out the head, the period, and the closing parentheses is we get 3. Okay? So to take another, to do that without all my writing, substitute 3 as x in the head and in the body. Throw out the head and the separator, and that leaves you the expression 3, which when evaluated just returns 3. Okay? And you can do some more fancy stuff. Like if in regular lambda calculus, each function can only take a single value. A single argument, I should say. In my lambda calculus that I wrote interpreter for, you can have an arbitrary number of arguments. So in the pure lambda calculus, if I wanted to do, say, some function that takes 2 values and just returns them back, that might look something like this. So I'm not going to do all the effort in writing out the lambda because I'm lazy. So this function takes a value x, and it will substitute that x, the value of it, in here in the body of this other function. So once it's done getting x, it will return a function to get y. So it'll get the next argument. This idea of using functions that return functions to get the next argument is known as currying. Okay, it's how we get it's how we have multiple arguments in functional programming. But in my lambda calculus, we can shorten this to make it look nicer. We can say lambda x space y dot xy. So you don't have to concern yourself as much about currying. So let's use this on 0 and 1. In this case, these are 0 and 1. Since functions are the only values that we have, they don't mean anything. They're just names. Since we haven't defined what they're equal to, they're just names in and of themselves. They have no meaning or value. Okay? So there's the digit 0 and the digit 1. So let's go through evaluating this function. So we substitute 0 for x. So we have something like this. So 0 has been used, and 1 is left over. Now we have to substitute some value for the y's. So let's do that now. We're left with lambda 0, 1 dot 0, 1. And we've consumed both 0 and 1. Now we need to throw out the head and the end parentheses, and we're left with 0, 1. Pretty simple, right? Now, this simplicity is, how do you say? It's deceiving. Because you'll think to yourself, oh, Alistair, this is so utterly simple. How do I do any sort of practical programming in this? Surely I'm unable to do any sort of programming in this, right? You're wrong. We can program in the Lambda Calculus. And I'll show you how. We're going to do, depending on how much time I have, I might pick this up later. We're going to define the natural numbers. And if you don't know, the natural numbers are all the numbers from 0 up to positive infinity. So plus inf for positive infinity. Okay? So now this, I'm going to have to bring up paint again. God damn it. Okay. So I'm going to do some black magic. I'm going to come up with a way of defining numbers. And now, a lot of this, I didn't come up with this way of how's it called? Describing natural numbers. I did not come up with this method. Alonzo Church and all of his pals did. But if you think about it, when counting, one way that we can do it is by, so we have some function f, okay? And some value x, okay? One way that we can do counting in some abstract, weird way is some number represents the number of times we apply f onto x. For example, 0 would take an f, some function, an x, and all it would return is x. Because it uses the function f onto x 0 times. Now by that same token, now some of you might be already seeing where I'm going with this, 1 can be defined as applying the function once onto x, right? That's cool, but what about 2? How would we do that? Well, that's also really simple. 2 would be applying the function f onto f of x. So we apply f onto the result of applying x to 1, okay? So what's 3? You're all really smart people. I'm sure you can see the pattern by now. You say, oh, 3 is f of f of x. So we apply f, some function, onto some value x. Then we apply that function 2 more times. So the sum total, the total number of times that we've used this function f, 1, 2, 3 times. Therefore, it's the number 3. Okay. So let's make our first number in the Lambda calculus. So I'm going to open up this, and then I'm going to open up my editor. So I'm going to say, very dramatic, yes. So since on my keyboard I can't enter in the lambda symbol like a normal person, instead of lambda for function, we do an open parentheses and a /. That is for defining functions. So 0 is some function that takes some other function, f, and a value for that function, x. We have the period for the separator between the head and the body, and all we do is we return x. Now, we have to end that off with a semicolon. Every statement, like I said, ends with a semicolon. So that is 0. That's pretty sweet. Let's open up the REPL. And here's something pretty neat. So you can load in your programs so you can use them, or any variables that you've defined in them. So this file that I'm working on is called tut, so I'm just going to load tut. No errors occurred, so everything's good. So I'm going to make a function that's going to go, what is the value of 0? What is 0? And it says, well, the identity function applied to 0 is just 0. Okay? F of x, this is the same thing as doing f of x equals x and substituting 0 for all of the x's. It's just 0. Okay? So that's pretty sweet, I guess. But another cool thing, if I just enter in the function, which is what 0 is assigned to, you know, f of x dot x, or not. Okay, we can not do that. I guess we'll have to use the identity function on that. There we go. So if I ask, hey, what is this function, you know, identity of this function, it says that this function is the variable 0. So that's kind of neat. And that'll come in handy when we're doing math, okay? So that's cool, I guess. And you're thinking, okay, well, I can make all the other numbers. You know, 1 is just f. It's a function that takes f and an x and does f of x, right? That's pretty simple. Neat. And then, you know, 2 is x, and then we apply f onto f of x. Okay? And that will work, but I don't know about you, but I don't want to have to type out all of this stuff when I want to make a new number, okay? And we're going to have to define our numbers. That's the downside to the Lambda calculus. But how would we define a function? So let's think about something. Let's open up my Magic Paint. What I want to do is I want to make some function that will take in some number and it will return me n plus 1. So the successor of that number. So for example, the successor of 0, so 0 plus 1 is 1. 1, the successor of 1, that's 1 plus 1, that's 2. Now you can see, if we make some function that adds 1 to a number, we might be able to use that to make addition. And we'll get to that later. But first off, let's focus. How can we define some function that returns n plus 1? Well, the important thing here is to remember that functions are defined in such a way where it's, you know, it's a function. I'm sorry, I worded wrong. We need to keep in mind that some number is defined like so. Takes an f and an x. It applies f of dot 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 f of x, or you know, dot 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 Okay. So you can see that a function is defined where we apply f onto x, or the result of it. We apply f to x n number of times. Okay? So, if we really think about it, all we have to do to get n plus 1 is to apply f one more time. And then this would be, this whole thing would be n plus 1. Right? That makes sense. If this was n number of times, if we applied this function f n number of times, and we apply that function one more time, we use that function, we call it one more time, we're going to get n plus 1, our number plus 1. So, I'm going to make a function called successor. I'm going to call it suck as an acronym because I am a lame goose. So this is going to be really tricky. Well, it's not that tricky, honestly. So this takes some number that we want to add 1 to. It takes some function that we're going to apply onto an argument, some value x. So we're going to apply f, we're going to call f one more time onto n of f of x. Now remember, every number takes an f and an x. It takes some function and some value for that function. Okay? So, since n is a number, if we feed it f and x, it will give us the result, like say 0. So if I had 0, f and x, this would give me back x, but then we would call f one more time onto that value to get 1. Okay? It's a little confusing, but let me show you that it works. So we have that. All we need is 0 in this case. So we're going to make a function called suck. This function takes some number. It takes a function to use and a value for that number. For that function, I should say, excuse me. We're going to call f onto the result of using our number with the function given and the value for that function. So we'll apply this function f n number of times and then one more time. So n plus 1 times. Now, I'm going to load in my program. And so we know what 0 looks like. You know, 0 is f x x. It applies f, the function, it uses the function on the value x 0 times. You can see that's 0. But, so let's ask, what is the successor of 0? Okay, this it doesn't preserve the parentheses when you're looking at it, but this looks interesting, right? We're saying that 1 is the result of applying the function, using the function f onto 0, the number 0, with the function and that number. So we apply it 0 times, we use the function f 0 times, and then we use the function f 1 more time, which means it's 1. Bam! So look, now I can go 1 is the successor of 0. 2 is the successor of 1. 3 is the successor of 2. 4 is the successor, holy crap, of 3. Let's 5. 5 is the successor of 4. 6 is the successor of 5. I'm going to define all the 0 to 10. So 7 is 6 plus 1. 8 is 7 plus 1. And 9 is 8 plus 1. And finally 10, that is 9 plus 1. So these are the first 11 natural numbers. Oh, and if you haven't guessed, this hash symbol is what a comment looks like. You can only use comments inside of your own programs that aren't in the REPL. Okay? So now what I should be able to do, I should, once I load in all the functions, I should be able to say, hey, what is the successor of 0? You know, what's 0 plus 1? That's 1. What is 1 plus 1? That's 2. What is 5 plus 1? That's 6. What's 9 plus 1? That's 10. But here's the thing. It only knows what 9 is. It only knows what 10 is because we've defined it. We've told it what 10 is in our program. If we ask, what is 10 plus 1? It's going to respond to us with, it's the result of 10, applying using the function f 10 times, and then using f 1 more time than 10, so 11 times. Okay? So that's how you read numbers like that. So by the same token, the successor of the successor of the successor of the successor of 0, 2, 3, and then with the semicolon, is 4. Holy crap, it's so smart. Because 0, 1, 2, 3, 4. Isn't that neat? That's all well and good, I hear you saying. But Alistair, oh, Alistair, I want to be able to, like, add numbers. Okay? How do add? Alistair, how do add? Me want add. Me want add. How add? Me. So dumb. Okay, so now. Actually, no. We'll wait before we do full-on addition, because we want to be able to do subtraction as well, right? So what we're gonna add is what we're going to define next is the opposite of the successor function, known as the predecessor. If someone says you're taking after your predecessor, that means you're taking after one of your parents, or someone who last worked at some job that you're working at, right? So, the predecessor of some number, n, is equal to n minus 1. So, what is the predecessor of 1, well, that's 0. The predecessor of 9, that is 8. The thing is, since we're working with the natural numbers, the predecessor of 0 is 0. 0, since there are no negative numbers, 0 doesn't have a predecessor. So keep this in mind. Now, at first glance, you're gonna try to think, okay, how do I do subtraction? How would I do that, Alistair? I'm very confused, scared. Well, if you think about it, if you really think about it, we're using f onto f dot of f of x dot. So we're applying f n times. We just need to knock off this f so that it is n minus 1 times. So what is what is one way that we could do things? Well, what we can do is we can count up to our number n. So say n is 2. Oh lordy Lou. Say our number's 2. What we can do is we can count right up to, but right before we get to 2. So 0, 1, and then we'd stop because 1 plus 1 is 2. Okay? But again, this isn't immediately obvious how you would do this in the Lambda Calculus. So let me do it another way. Let's imagine a function f. We don't know what this does, but let's imagine a behavior. Now, if you're comfortable with lists in Python, then this is going to be a little bit more comfortable to you, okay? So I'm going to equate this to lists in Python. Imagine that we feed this function a list of 2 elements like this. And what we want it to do is you'll take the second value, put it into the position of the first value, and then in the second position, we'll add 1. So what we'll get, in this case, 0, it will just plop 0 down here, but it'll take 0 and add 1 to it. So we will get 1. But then if we think again, if we apply the same function again, this will go over here, we'll get 1, this will go down here, and we'll add 1 to it. So we'll get 2. But hold on a minute, you might be thinking to yourself. If this function, oh yikes. Yeah, let's rewrite that. If my function, f, imaginary function, if it, when we keep applying it, it counts up this one, and this one is the last value, then if we really think about it, this number, the left number right here, is going to be n minus 1, and this right value is going to be n. Look at that. So, if we have a list and some function, we just need to define a function that will make a list of 2 elements, where it takes the second value, replace it for the first value, and take that same value and add 1 and store it in the second value. Then we can count. But how the hell do we do lists? Well, if we want to do lists, we're going to have to take a slight detour. And we'll be right back to the predecessor function, don't you worry. But before we do that, we're going to talk about booleans. 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 Yep. This is all related, trust me. So, booleans. Booleans in some language are true and false. And they allow you to choose between two things, X and Y. You know, do this if true, do this if false. False, okay, between X and Y, we'll always choose Y. But true will always pick X, the first value. Imagine that this is the then portion, and this is the else. So, if true, then else. If we give it true, it will do the then. If it's false, however, it will do the else. Right? Okay, so let's see if we can define booleans in the lambda calculus, okay? It just needs to pick between two values, okay? So, remember, true will take an X and a Y, and it will return X. False will take an X and a Y, but it will return Y. So let's see how we can define that in the lambda calculus. This should, for those of you who are inclined, this should kind of look pretty simple. So we're going to have true. This is a function that takes an X and a Y, and it just returns X. But then, false, this is a function that takes an X and a Y, but it returns Y, so it returns the second value. Let's test out if this works. So to test this, I'm going to call true, and if it does what we think it does, it should return 1. It does. False should return 0. It does. Okay, so let's quickly run through how this works. So I'm going to write out true. Alright, let's start running this. So we're going to substitute X for 1. We're going to replace all X's for 1. In both the head and the body. And we have 0 left, and we need to get the value of Y. So we have lambda 0. And then we throw out the head and the body, and what we're left is... Mistake were made. And the result is just 1. Because we put X in the body, that means we save it after we're done stripping off the head and the body. Okay, that's pretty neat. So then, it should be pretty apparent how the false function works. Substitute X for 1, but you don't do anything with it, and so you have 0 left over, so you do lambda 1, 0, dot 0. You strip off the head, the body, and the end parentheses, and you get back 0. Bam! Boolean true and false. That's pretty cool. Now, we're not going to talk about Boolean operators just yet, but that'll get really important when we start talking about what's it called? Relational operators. which you can bet I'm going to talk about. So, real quick, let's talk about lists. Or at least what's going to be called a pair. A pair is a list of two values, which will have an x and a y. Okay? So to make a pair, we're going to use the word cons for construct. So given an x and a y, it will return to us a pair of x, comma, y. So list of x and y. Okay? But then we're going to also need to define value operators to get x and y. So we're going to have car of a list of x and y. And this is going to return x. And we're going to have another one called scatter. It's going to take a list of a pair of x and y and return y. Now, it's going to be really crucial. Keep this in mind. And let's talk about how we would make a pair. So cons is a function that takes it'll take a let's think for a moment. It will take a it's going to take a B, a C, and then an A. And then it's going to run A, B, C. Okay, so let's look at this. So if I do, oh yikes, forgot my lambda symbol. So if I do lambda B, C, A, B, C, and I wanted to make a pair, I should say, of 0 and 1. So I wanted to have 0, 1. I would have it look like this. So what we're going to do is we're going to substitute 0 for every B. And we're going to get lambda C, A. Oh no, I shouldn't do that. I should make it more explicit. So we've used up B. So we have A, 0, C. Okay. So we got the first element done. Now we need y. So we substitute 1 for C. And what we get is a new version of the function that has 0 and 1 used up, but we still need A. Now I'm going to do some black magic. Since 0 and 1, those variables have been used up, we can just erase those. And that leaves us with a new function, lambda A of 0, 1. So this is a pair. Now the thing is, what we need to do now is actually let's prove that this actually works, right? So let's go into this, our little REPL thing, and we're gonna do let cons. So we're gonna test our function in here. So it takes a B, it takes a C, and then an A, B, C. Easy. Now let's ask, what happens when we make a pair of 0 and 1? You can see that we get exactly what we drew here. Lambda A dot A01. Here. Cool, but how do we get A out? Well, for those of you already ahead of me, since we know our Boolean operators take two values and return one of them, if I take this list, this pair, and then I feed it in a Boolean as A, it will then pick between returning 0 or 1. So true, since it returns the first value, it will return 0. And if I feed it false, it returns 1. Let's real quick go over that. I'm going to write out the function form of true. So now what we're going to do is we're going to feed in this function as A. Okay? So after replacing A for this function and removing the head and the body, we're left with lambda x y dot x, so true, 0, 1. And since we can already see it takes an x and a y, we're going to have lambda 0, 1 dot 0. And then when we strip off the head and body, we're going to be left with 0. It returned the first value. Isn't that neat? So then by the same token, I do lambda xy dot y, which is false, and we substitute this for A, and we replace it for A and strip off the head and tail. I just don't want to write it all out because it's a bigger function. We're going to be left with lambda xy dot y 0, 1. And then we run this, we'll get lambda 0, 1 dot 1. Remove the head and tail, head and the closing parentheses, we go 1. So return the second element of the pair. So now that we know what happens when we feed true and false as A, the last value in a pair, what we can do is we can define car and kadir, which will return the first and second values of a list. I should say pair. Remember, so car of x and y will return x, and kadir xy will return y. So let's do that now. So car is going to be a function that takes a list, a pair, I should say. I'm going to represent that as a P for pair. And it's going to feed true as A, the last value, into the pair. So let's check that out now. So instead of feeding it false from the right, we just take this list and go car of this list. And then it should give us 0. And it does. And if you ever want to see the steps that your program or that some expression takes into getting the result, if you type in the REPL hash symbol and then debug on, they'll turn on debug mode. And if I type this out now, it shows me all the steps. So 0 is every sub-expression that I'm evaluating. So 0, in this case, we're evaluating this entire expression. And then 0 again, the sub-expression that we're going to evaluate is cons 0, 1. So make a list, a pair of 0 and 1. So then it starts going, it replaces the actual function for the word cons. It substitutes 0 and 1 as B and C. And we get our pair. Then we continue from here at 1, and we're going to take the first value of this list. So we get the actual function of that name, car. We feed in that list, and we have P, our list, and true. So our list and true. Substitute A for true, and we have true 0, 1. Make true into its function form, and substitute x and y for 0 and 1, and return 0. So this could be really helpful if you want to see how things work, but it can get pretty crazy for bigger operators. But so that's car. Cadir is pretty simple too. Take a pair and return that pair where the last value A is false. So if we do our earlier example, if we type in Cadir, it'll return 1. Hey, we just made pairs. Now let's add those functions to our text file. So I'm going to call, so we need cons to make a pair. Takes a B, a C, and then an A to choose between each value. A, B, C. Then we need car, which takes a pair and gives true to that pair to get the first value. Now Cadir, take in a pair and feed in false. Okay. Now if we close that out, open up the REPL again, and I load in the program. What is the problem? There is some problem. Really? Okay. Does it help if technical difficulties? Okay. So that worked, for some reason. Whatever. We should make sure that making pairs still works. You can use parentheses to group things together, just so you know. And so if I ask what the first value is, I should get 0, I do. And if I ask what the second value is, I should get 1, which I do. So everything's working correctly. Now, back to the predecessor function. We now have what we need to make the predecessor function. So let's go back to what that was. Okay. Now, oh no. Let us think a big thinky. Now remember, if we apply this function onto a pair 0, 0, what it will do is it will add 1. It will make the second element into the first element, and it will drop this one down and add 1. So this will drop down, this will become 0. It will add 1 to it, making it 1. But if we apply f onto that, it will drop down 1. It will drop down 1 and add 1. So we'll have 1, 2. So let's try to formalize this. Let's think about it as a function. Okay. So it's some function p. So this function takes a pair. And what it's going to do is it's going to construct a new pair where the first value in the pair is the second value of the old pair, and the second value of the new pair is the successor of the second value of the old pair. So let's try feeding this function cons 0, 0, right? So let's use this as guidance. So it's going to be cons Kadir P, successor of Kadir P. No errors. So now, if we give this function the pair, that is not 0. So if we give it this pair, it should give us 0, 1. Look at that, it does. But now, let's try experimenting. So we have this function. Let's call it trans for transform. Okay? Save that, no errors. So if we transform the pair 0, 0, we get 0, 1. Okay. If we transform the result of transforming 0, 1, what will we get? 1, 2. Takes 1, puts in the first value, and also puts it in the second value, but plus 1. So if we do this a third time, if we use the function transform one more time, we have 3 and 3 minus 1, 2. So I have a question. You might be thinking well, you might have a question. You might be going, okay, Alistair, that's cool, but how do I use this to make the predecessor function? Easy. Since a number takes in a function to use that number of times, if I say I want to use the transform function, if I do 3 and then the transform function, this says I want to use the transform function 3 times. Let's take a look at that. So you can see that we're going to use the function transform onto the result of using the transform 2 times onto x. So now, if the x that we give is 0, 0, you can see that what we get is 3 and 2. Look at that. So now you might be saying, okay, to subtract, we do 3, we do our number onto the transform function with the pair 0, 0, and then we take the first element, the first value in that pair, which will be n minus 1. So we're saying, what is the predecessor of 3? That's 2. What is the predecessor of 5? That's 4. What's the predecessor of 1? That's 0. What's the predecessor of 0? That's 0. Look at that. So let's add that full definition into our program. So the predecessor of some number is, we take in that number, and we're going to take the first element of the new pair that we'll get. The way that we compute this new pair, this new number, is by applying some function n number of times to the pair 0, 0. The function that we're going to use n number of times is a function that takes in a pair and constructs a new pair where the first element is the second element of the old pair, and the second element of the new pair is the successor of the old element of the old pair. So this function should return the predecessor of some number. Predecessor of a number. Okay. To test that out, let's just load in our program. So, we ask, what is the predecessor of 5? It's 4. What is the predecessor of 3? That's 2. What's the predecessor of 0? That's 0. What's the predecessor of 10? That's 9. Look at that. We have made the predecessor function. Look at that. Now, we're super close. Now, this is gonna be fun. I think. How would we? Let's do addition now. How do we do addition? Well, maybe let's draw a picture. Try to help us think about it. If we think of it maybe in terms of walking or something, if I walk 1, 2, 3 steps, if I wanted to walk 5 more steps, I just immediately walk 5 more steps. So, 8, we have the sum total of all the steps taken is 8 steps, because we took 3 steps, and then 5 more steps, which is 8 total steps. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. 8 steps. So, what we need to do is we need to have our number n, and we need to apply the successor of that number. So m, we just need to apply some function onto n m times. So what this says is we're going to make a function that we're going to do f m times, and with that new function, we're going to then do n times and then x. That makes no sense. Oh my god. Whatever. Let's I might have this one wrong. Let's see. So if we have okay, so we just added 1 and 2, and now what we want to do is we want to take the successor of 0 that many times to get the number. So this should give us 3. Instead, we get this evil monster. What is it? Is it maybe I got it wrong? Maybe it's actually okay, let me show you how I do know how to do it. Okay. Let's redefine the transform function. That's a tad embarrassing. So we're gonna make a new list. Oh, come on. Oh, crash me. Make a new list where it's the same value, and we take the successor of the standard value of the old list. There. So one way to think about it, we could do 3. We're going to apply the transform function onto the result of using the transform function 2 times. Okay, so we're going to use the transform function 2 times and then 3 times, yeah?
Sorry. I have a work Christmas thing I'm going to now. Grandma and Grandpa are picking you guys up to take you to dinner. So if you could be ready about 5 to 7 and watching out for them so they don't have to get out of the car and come to the door. Please.
Okay.
And if you could take a key with you so you can lock the door when you leave. The house isn't left unlocked, I'd appreciate it.
Okay.
Okay, we'll be back in a while.
Have fun. So that's my cue to leave. I guess I'll come back later, maybe. But so this is how you will do the add function. Here, let's do add. We'll just name it real quick. So it takes an n and an m. We take n, we apply transform n number of times, m, and trans on take on 0, 0, 2, 3, bop, bop. Add 1, 0, and 1. That's 1. Oh, ooh, we're not done. You take all this, and you take the second value, because the first value will be n minus 1 of the sum. So add 0 and 1, that's 1. 1 and 1, that's 2. And then 3 and 2, that's 5. So I guess I gotta go. I'll see you guys later, maybe. I hope you enjoyed. Auf Wiedersehen. Oh, did it not go back on because it crashed? Oh no!